Let's talk about some science and some space stuff. I was actually shared this by our good old friend over here, Cell, who shared with me that the space telescope Euclid has given its first images back, and they are stunning. So I wanted to talk about both Euclid itself, the actual telescope, talk about what it does, what it's going to look for, talk about what it's seen so far, and the images it's produced, and talk about why they're important. The images have just been released, which means that the scientists are still working on them, they're still being reduced, and interesting science questions are starting to be posed. So hopefully we will start to see some more interesting questions later, and more interesting answers later as well. We got our first images back from Euclid, which is part of the European Space Agency's Euclid mission. I'm curious, I think I made a typo. I think I said ESO instead of ESA. I did say ESO. Skitty. Oh well. Oops. I'm part of the misinformation on Twitter now. Oh well. I'm going to be banned from twitter.com. They got their first images and they're in full color. They're very, very beautiful. But before we talk about the images, I want to talk about the actual telescope itself. We've actually talked about Euclid before. I found some images from the Wikipedia page that are actually images that I've used to talk about Euclid before. So I'm like, oh yeah, I did talk about this. So let's talk about Euclid. This is Euclid, at least this is what it looks like on paper. The actual telescope looks basically exactly like this. It hasn't changed. This is the original science book from 2010. Back when they were proposing the project, so 13 years ago at this point, which is, God, I feel old. But in any case, this is what the telescope looks like. It's got a bunch of little pieces all throughout that are all of interest, but we're not really going to talk too much about any individual of them, but I kind of just wanted to show off the telescope itself. Talk a little bit about kind of what it's designed to do. So long story short, this is a telescope that is designed to look at a huge swath of the sky and look at a whole bunch of different objects throughout that portion of the sky. The number they throw around a lot is they're looking at 1/3 of the sky, which is nuts. That's a whole lot of space. Like a whole lot. It's so much data. But this thing is positioned out in L2, which those of you who know about JWST, and maybe Gaia, if anybody here is familiar with Gaia, should know that we have telescopes out there already, and I'll talk a little bit more about L2 in just a little bit, because I get a feeling that a lot of people don't really know what L2 actually is, and I figured this was a good time to describe it. But that telescope is out there with the sun shield facing the sun for obvious reasons. That sun shield serves two different purposes. It can A, block the sun from heating up the instruments because they need to remain cold and have a very, very low amount of thermal noise in order to get the images that we're trying to get. And they also give a little bit of power to some of the systems on board, so it's basically a giant solar panel on the back. They've also got a few different thrusters that can actively adjust the telescope's orbit and its position in the sky, which allow it to both look at different places in the sky as well as maintain its orbit around L2. On board, it's got two different cameras. It's got a visible camera and a near-infrared camera. It basically does what JWST and Hubble did, whereas Hubble looked in the visible and JWST is looking in the near-infrared. It does both of them, though its science objectives are slightly different than both of those telescopes. So it's worth noting that yes, we can already look in these bands, but this is meant to do more of a survey, whereas JWST is looking at individual objects. Very different science goals here. Both of these telescopes are both actually looking at similar science questions. The similar science question that this is trying to answer to JWST is all about dark matter and dark energy. So it's trying to figure out what are these weird dark substances that do not match physical matter that we know otherwise, that we know must exist in the universe. How can we categorize them? Where do they lie? And how do they change as we look further back in time versus where we're looking in the modern day? So we're looking at galaxies billions of years away, and we're looking at galaxies millions of years away, and we're comparing them to say, okay, how did these morphologies change over time? Can we learn anything about how dark energy versus dark matter is contributing to the situation? How does the cosmology change? All that good stuff. We're looking at all of that. Effectively, this thing is making a three-dimensional map of the universe, with a third dimension being time, because as we look further back, further away from us, we are getting a ticking back of time. So we're looking in 2 dimensions of space, and 1 dimension of time being how far away we go, because the further away we go, the longer it took that light to get to us, so we're looking back in time. That's what this thing is trying to do. These are some of the images that I talked about before. You might remember these. These are some of the near-infrared images that it took in its early test imaging. You might remember this one being the GRISM apparatus, where it takes every single individual point of light and separates it based on wavelength. It can be useful for doing spectroscopy. And then here's what it looks like in the visible. And all of these are effectively squares that the thing takes, then it moves, it takes another square, then it moves, takes another square, moves, takes another square, and it basically tessellates an entire section of the sky, which is very, very cool. And it can give us very, very detailed pictures while also keeping the entire structure within view for some of the larger things that we're looking at. It's a very neat instrument. So let's talk a little bit about the Lagrange points. I actually should have looked at this first. We have a few different objects out at the Lagrange point L2. The three that are out there right now are JWST, which I talked about at length, and Gaia, which I haven't really talked about, and now Euclid is out there too. This point out here is a point beyond the Earth. Basically, we can draw a line from the Sun to the Earth and then keep drawing that line, and you'll eventually reach this point called L2. L stands for Lagrange, which is the second Lagrange point. And more or less, and I'll explain how this works in just a second, these points act sort of like attractors in those locations. So you can have an object out here at the Lagrange point, and it will be relatively stable. So we can have JWST and Euclid moving in these orbits, and in theory, they should just keep doing that until they're perturbed somehow. Now these are unstable equilibria, which means that if these do get offset a little bit by dust or some other thing like solar wind, they will eventually fall off of L2, which is why we actually need the thrusters in order to make those tiny little adjustments. And the reason it works is more or less a trick of the math. I'm not going to go into the math, trust me, it works. But what we have here is we have what's called a contour diagram. And what these contours are showing us, these are showing us gravitational potentials. So we have a giant gravitational body in the Sun and a smaller gravitational body in the Earth, not to scale, of course. These are very much not to scale. And then we have the Moon, which we're going to ignore for the purposes of this. It does have minor effects, which is part of the perturbation that we need to worry about when we're dealing with things actually orbiting L2. Like I said, it's unstable, so if it gets perturbed in any way, shape, or form, it'll fall out unless we correct for it. The Moon is one of the things that can do that, as are the other planets. You'll notice that there are 5 of these, L1, 2, 3, 4, and 5. All of these points are places where the gravitational forces and rotational forces effectively cancel out, meaning that something moving in an orbit around where those points go, because these points move with the orbit of the secondary body, they should stay there. So if I put something right here on this green dot over at L2, and we set it in a circular motion, so it maintained this line between the Sun and the Earth, it should stay there forever, in theory. But you will also notice there are all these little arrows, and these little arrows show us the direction of the potential going downhill. And since this has a saddle pattern where the stuff on the top is pointing in, the stuff on the bottom is pointing in, and the stuff on the side is pointing to the left and the right, if this thing that is at L2 or L1 or L3 gets perturbed, it'll fall off down that potential. So it'll either fly out into the expanse of space, or it'll fall into the Earth, or the Sun if you're talking about L1 and L3. The reason it works out in L2 is because you have the gravity from the Sun and the gravity from the Earth. They are effectively fighting against the centripetal force experienced by the object out here. So everyone's experienced this, I'm sure. If you're in a car and you turn, you feel like you're being pushed against the side of the car. This isn't a real force. You're not actually being pushed against the side of the car. It's that the car is moving to... Oh, sorry, microphone. You're not actually feeling a force. What you're feeling is the fact that the car is moving in one direction and you don't want to. Your body wants to keep going straight, but the car is forcing you in the other direction. In reality, the real force is pushing you inwards, towards the turn. That's the thing keeping you in your circular path, but you will feel like you're being pushed out. It's called a virtual force. And this thing out here feels a virtual force trying to basically rip it out of its orbit and fly off into space, and the thing keeping it there is the gravitational force of these two bodies. At L2, this is the location where the centripetal force, the fake or virtual outward force, is completely and equally cancelled by the inward force of the two bodies it's orbiting. Long story short, this is a point of equilibrium. So is L1. This is where these two gravitationals plus the centripetal force of the orbit cancel out. L3 is the same thing. Centripetal force is cancelled out by the Earth and the Sun. We're over here at L2, and what this allows us to do is effectively orbit this point as if it were a gravitational body, because right there is a static, well, not static, it's a dynamic equilibrium, where all of the forces cancel out. So when we're playing around in that area, it should always tend towards this point, plus or minus the perturbations, which is why we have all of the corrective measures, like all of these cold gas and chemical thrusters. So that's your sort of spark notes on the Lagrange points. It's a lot more complicated than that when you have to worry about multiple bodies other than just the two that we're dealing with, i.e. the Sun and the Earth. If you add the Moon in there, it gets complicated. If you add the other bodies of the solar system in there, it gets complicated. If you add things like solar wind and general relativity, it gets more complicated. Long story short, though, we can pretend that these points are stable places that we can have things orbiting, which is how we were able to put all these telescopes out there, which is awesome. We also do have another, it's not a scope, I believe it's a solar observatory for solar wind activity here at L1, which is also very cool. Let's actually look at the images. The first image that Euclid took was of something called the Perseus cluster. This is the Perseus cluster. It is a cluster of galaxies. You'll notice that if you look closely at some of these individual objects, they are actually spiral galaxies, and these other weird globs are what we call elliptical galaxies. They're a whole bunch of stars in a giant bubble, basically. So why is this important? Why are we looking at this? Well, we're looking at this because it is a structure that shouldn't exist according to its own gravity. The only reason it exists is because of the extra gravitational force created by the dark matter that we presume is inside of it. So we're looking at objects like this over time to figure out how they evolved, to figure out what they looked like in the early universe versus the late universe, and to try to learn about the effect of dark matter and the distribution of it in these types of spaces. So that's what this is all about. But this is a beautiful image. You can also get the full res images from the website. Let me post this in case anybody wants it. So that's Perseus. This one is intensely beautiful. This is a spiral galaxy, and similar, I didn't realize there was that option. Oh wow, look at that. Similar to the galaxy clusters, this structure should not exist in the form it does. This looks a lot like the Milky Way galaxy. It's a slightly barred spiral, and it shouldn't keep the rotational curve that it does. Things that are outside on the edges of this spiral are moving faster than they should. There's some amount of extra mass in here, which again, probably dark matter. Real color or assigned color? Good question. I'd be willing to bet it's assigned color. Nothing actually looks like this in the universe. Let's see. This is near infrared, so it's 100% assigned color. Yeah, almost every image you're going to find in astronomy is going to be assigned color. Look at the level of precision we're getting, and these are not the science images, I should note. We can resolve individual bright stars. Like, look at this. These are individual bright stars within this galaxy. We can see individual stars inside of the galaxy arms, which is frigoraphs. And this is not the full science image. This, in fact, is just the web image. We can actually get the full TIFF here if I wanted to. It's a lot, so I'd have to unpack it, which I'm not going to do right now. We're looking at this image because we want to learn a few different things. We want to learn how galaxies like this are formed, so we're going to look at the morphology of these galaxies as we look further back into the early universe, as well as the dark matter concentration within these galaxies. Which we can find by seeing how these galaxies lens objects behind them. We can also learn about how stars form in these galaxies and the actual populations of different types of stars within galaxies like this as time goes on, to learn about stellar evolution and galactic evolution. Here's another great one. This is a globular cluster. I talked about elliptical galaxies just a second ago. This is not a galaxy. This is a set of stars within our galaxy. I believe this is 7,800 light years away. Yep, I remembered correctly. And this is a globular cluster of stars. So it is, as the name would suggest, a glob of stars. So each of these dots is an individual star within these clusters. And similarly, the mechanics of these might be governed a lot by dark matter. And we basically want to ask the question, as time moves on, how much are these governed by dark matter and dark energy in terms of the expansion of the universe and such? So each of these little bright spots is either a star behind it or in front of it, but largely stars within this globular cluster. There's so many of them, and we can resolve most of them, which is, again, absolutely insane. This telescope is wild. Here's a galaxy in the background. That's pretty cool, actually. So we can look at globular clusters too. And I think probably my favorite of the bunch, the good old Horsehead Nebula, which I'll look at this image. This is a very, very famous thing to look at. Almost every telescope will look at this. This is a stellar nursery. Effectively, it's a whole bunch of gas. This is a nebula that is starting to coalesce to form stars. This is some of the most intensely interesting stuff to look at in the early universe. This is basically telling us, how did all the bright stuff form? This is how all of the stars in the universe, theoretically, formed, was just these collections of dust, eventually collapsing and forming stars. Like I said, this is giving us a lot of information about how stars are formed, how stellar evolution begins, and now that we have this unprecedented resolution, we can start to find things called hot Jupiters, effectively gas giants that are very, very close to getting heavy enough to start fusing hydrogen, and then will become stars. And they pop out these cool little bubbles around them, which make them sometimes easy to find. There's another one right here. Look down here in the bottom right. You can see the tiny little bit, this tiny little window that we are looking at in this entire image. This image is gigantic. It's very, very cool. I really, really like these images. Hopefully there's going to be a lot of good science coming out of this, how galaxy clusters are forming, how galaxies themselves form, and how they actually have dynamics, globular clusters and the individual stars within them, and the early birth of young stars. There's so much to talk about. Euclid's got a lot of cool stuff going on, and I really can't wait to see what comes out of it. I'm going to keep my eyes on this. Thank you, Cell, so much for sharing this. Always love it when people share this kind of stuff.